All right, welcome function folks for lesson 2.4 on oblique asymptotes. Last day we were talking about horizontal asymptotes, and this is a continuation of that discussion, which is a pretty interesting discussion, as we'll see. The 3-minute review here is to practice some of these skills. The idea of now that I'm given a rational function, I should be able to pick off the vertical asymptotes and horizontal asymptotes fairly quickly. The vertical asymptotes, remember, happen where the bottom is 0, and when's that? X equals 4 is the equation of the vertical asymptote. Horizontal asymptote, we think about the degree, and since the top and bottom are both degree 1, then we pick off the leading coefficients. The horizontal asymptote is a half. That's all we're asked to do. We're not asked to sketch it or anything like that. So on we go. Vertical asymptotes are when the bottom is 0. Little quadratic equation, it factors. Will we ever get it? So we have to do factor theorem on the bottom? Oh, I would never do that to you, would I? Yeah, of course it'll happen once in a while. Not very often. Usually it's linear or quadratic on the top or bottom. So two vertical asymptotes, because there's two spots where the bottom's 0. The horizontal asymptote, well, notice the top is smaller than the bottom. The bottom has degree 2, the top is degree 1, and in fact, we get a horizontal asymptote of y equals 0. The next one, vertical asymptote, is when the bottom is equal to 0, and this is a special case of difference of squares factoring, and I get x equals 1 and x equals -1 as my vertical asymptotes. The horizontal asymptotes, both top and bottom have the same degree, and do I care that this one has an x and this one doesn't? No, because they have the same they have the same degree 2. The other terms don't matter. I just pick off the horizontal asymptote y equals 2 over 1, or just y equals 2. And finally, the bottom vertical asymptote as when x equals 2, when the bottom is 2. And the horizontal asymptote since the top is degree 2 and the bottom is degree 1, we would say there's no horizontal asymptote. But this case here, no horizontal asymptote, this is degree 2 on the top and degree 1 on the bottom. Degree 2 on the top, degree 1 on the bottom. Something interesting happens in this special case where there's no horizontal asymptote, but the top is only 1 more than the bottom, and I want to show you that. Graphing calculator, there's the exact function, and I'm going to go, zoom standard, zoom 6, and we get, there's the vertical asymptote at 2, and we can see that there's no horizontal asymptote, that it goes off to positive and negative infinity on the left and the right of the graph. But something's going on there. It looks pretty straight. And in fact, and this is where we get to the note, number 4 from the warm-up, we knew that there was no horizontal asymptotes, and this is the graph. It's kind of got to change scale. It looks like there's a slant asymptote. Right? It looks like, in fact, if I were to cover that up, and of course you can't do this on your notes, it looks like a straight line. It looks like I've got a straight line asymptote here. That's not a horizontal asymptote, but a slant asymptote. And in fact, if I go back to my graphing calculator, I could probably guess what the equation was. Let's just guess and check. It looks, from the graph, it looks fairly steep. So I'm going to try, say, 3x. And I press graph. No, that's too steep, right? You see how the one that I put in there is too steep, so I might try 2x. There's my rational function. There's my slant asymptote. Notice that this is close, but it kind of crashes into the graph there. I'm going to move this thing down because it looks like it's getting close there, but I'm going to move it down 1 just so it doesn't crash in. Hopefully I think this will do it. There's my rational function, and there's my slant asymptote, a slant asymptote. And so that's what it says in the lesson here, that if I were to actually draw a graph of a line there, that this the equation of this line is y equals 2x minus 1. It says, gives the equation y equals 2x minus 1 on the TI-83. But how in the heck would we get that? Right? I can't be guessing and checking slant asymptotes all the time. They don't happen very often anyway. How would I get it? And the answer is mind-boggling. It's amazing. We use long division, believe it or not. Watch the magic here, folks. So if I take my bottom of the function and I divide it into my top of my function, watch what happens. Divide, need a value that will get this to cancel out when I subtract. Then I subtract here and I get negative x, bring down to 3. Negative 1 is the next thing that works. Negative x plus 2, and that's amazing. Look at that. There's the oblique asymptote. Amazing. All right, fine. When we know that it didn't divide evenly, otherwise we would have had that weird case where if the bottom divides into the top, where's the function? The function, remember, this was the function. If there was no remainder, then this bottom part would divide evenly into the top, no remainder, and then we'd have a whole. But we know that doesn't happen. And in fact, when we divide, we get a remainder of 1, and the oblique asymptote is 2x minus 1. So why the heck does this work? And you don't have to worry too much about this, except for something as amazing as this. It's nice to have an explanation. Remember back when we did the long division, we'd write a division statement. In fact, we'd write the thing underneath is equal to the thing we're dividing by times the thing on the top plus the remainder, right? Well, notice that our function f at x isn't just this, right? If I divide by x minus 2, that's f at x, right? This is f at x now if I divide by x minus 2, but I have to divide this side by x minus 2. And notice that on the right-hand side here, what do I get? Well, divide this into this. I'm going slow here, but you'll see what I'm talking about. Divide this into both chunks. That's the remainder, isn't it? That was that remainder one. And over here, I think of this as then 2x minus 1 plus 1 over x minus 2. Now notice, this expression is equivalent to f at x. Therefore, f at x is equal to 2x minus 1 plus, and by the way, we'd never think of the function f at x like this because it's harder for us to see the graphs. But think of it this way. Think of as x going to positive infinity. When x goes to positive infinity, this goes to positive infinity, 1 over this goes to 0, doesn't it? This has a horizontal asymptote of 0. Then we think of that last term going to 0. And then what happens to the entire function? F at x goes to 2x minus 1. F at x behaves like y equals 2x minus 1 for x going to positive infinity. Or negative infinity, by the way. It works both ways. So that's why it works. All right. I'm going to pick up the one example that we've got left and the conclusions from this little talk in part 2.